Okay, everyone, welcome to the second section of our chapter. Now, in this section, we are moving beyond the main sequence and looking at what happens when stars like our sun starts to run out of fuel. So, this is the stage called post main sequence evolution. So, let's start with the first key idea. Now, every main sequence star spends most of its life fusing hydrogen into helium in its core. But eventually, the hydrogen in the center runs out. Now, what's left behind is a dense core made of helium ash. So, you can think of it like the embers left at the center of a campfire once the fire has burned through the wood. Now, at this point, the temperature of the helium core is still too low for helium to fuse into heavier elements. So, even though there's fuel there, the star cannot use it yet. The core is essentially inert, but it's about to change. So, here we can imagine the star's interior as a layered structure. A dense helium core surrounded by still available hydrogen further out. And this sets the stage for the next phase. So, what happens to that helium core when fusion stops? That's where gravity steps in. Now, with no fusion pressure to support it, the helium core starts to contract under its own gravity. And as it compresses, the gravitational potential energy is converted into thermal energy, so the core heats up. Now, this is a critical point. The star has not yet started helium fusion, but its core is getting hotter and hotter as it shrinks. So, you can think of it like squeezing a spring. The more you compress it, the hotter it gets. Now, this core contraction is what ultimately drives changes in the layers above it. So, while the core is heating up, the star finds a new way to generate energy in the surrounding layers. Now, a thin shell of hydrogen around the helium core gets hot enough to start fusing. So, you can imagine a fire spreading outward from the center of a log. The shell burns hydrogen while adding more helium ash to the core beneath it. Now, this process is very important. It produces extra energy which pushes outward on the outer layers of the star, causing the star to expand. So, it's the start of the star's transformation into a giant. So, even though the core itself is still inert, the star is not done producing energy, and the outer shell takes over. And this sets up a very dynamic period in the star's life. So, to summarize this slide, the star leaves the main sequence when hydrogen in the core runs out, the core contracts and heats up, and hydrogen fusion continues in a surrounding shell. Alright, now we just saw how the star leaves the main sequence and forms a contracting helium core with the surrounding hydrogen shell. So let's look at what happens next. And this is the dramatic stage where the star begins to expand into a giant. Now here, take a look at this image. It shows the internal structure of a red giant star. So as we discussed, the helium core is compact and heating up. But this energy doesn't just stay in the core. It pushes outward, affecting the layers above it. So the star ends up with a very small dense core and a bloated outer envelope. So you can see in this figure how the core is tiny in the center while the outer layers stretch far outward. And you can think of it like inflating a balloon. The inside is dense, but the surface expands dramatically. Now this is a major structural change. The star is no longer a relatively uniform main sequence star. Its interior is now very layered and dynamic. But the expansion is not just due to the core heating. Something else is contributing even more energy. The hydrogen shell surrounding the core ignites. And this shell fusion produces more energy than the star needs just to balance the gravity. So this surplus energy is what literally blows the outer layers outward. So imagine the star is so overpressured that it has to expand to release the extra energy. Notice the arrows in the figure pointing from the core to the surface. They represent the flow of energy pushing the envelope outward. So this shell fusion drives the star to enormous radii, much larger than it was on the main sequence. Now as the envelope expands, there's a trade-off in the star's outer layers. And the expanding in the outer layers requires energy. And this energy is absorbed in lifting the gas against gravity. So as a result, the surface temperature drops. So even though the star is brighter overall, because of its huge surface area, it appears cooler. And this is why the star moves into the red giant phase. Large, luminous, but cooler in temperature. Now again, this figure helps us visualize this. The core is still hot, but the surface has cooled and expanded. Now to sum up, the contracting core and the hydrogen shell fusion work together to push the outer layers outward. And the star grows massively in size, cools at the surface, and becomes a red giant. Alright. Now that we have seen how the star expands into red giant with a bloated envelope and a contracting core, let's see what that looks like in the chart diagram, which is the astronomer's map of stars' temperature and luminosity. First, take a look at this figure. Here we see evolutionary tracks showing how stars of different masses move after leaving the main sequence. So as the star's envelope expands, the surface cools. And on the chart diagram, a cooler temperature means the star's points shift to the right. And at the same time, the star becomes more luminous because its surface area increases dramatically. So this pushes its points upward on the diagram. So the neat effect of the red giant expansion is a movement diagonally up and to the right. Now here this figure shows this clearly. You can see the main sequence at the left and the giant branch exceeding to the upper right. Now here, notice the arrows traced in the path of the stars. It's like a road map of stellar evolution. But not all stars move along the diagram at the same speed. The time scale depends strongly on stellar mass. Now for a star like our Sun with one solar mass, the transition from the main sequence to the giant branch takes roughly 150 million years. And that's long, but still much shorter than the 10 billion main sequence lifetime. And for a massive star, say 5 solar mass, the same transition happens in less than a million years. And that's incredibly fast. So this is why even though giants are very bright and easy to see, they are relatively rare. They spend only a short time in this phase compared with the main sequence stars. Okay, now let's connect this to actual stars you might have heard of. Now as we said, medium mass stars evolve into the giant region of the chart diagram. And famous examples include Arcturus, Aldebaran and Pollux. So each of these stars started on the main sequence but moved up and to the right as they expanded. And the massive stars on the other hand move into the supergiant region. Stars like Rigel, Betelgeuse and Deneb are far larger and brighter. Betelgeuse, for instance, is a red supergiant with a diameter hundreds of times that of our Sun. So this HR diagram helps us visualize how mass determines where a star ends up in the post-main sequence stage and why giants and supergiants occupy distant regions of the chart diagram. Now to summarize, expansion and cooling move stars upward and to the right on the chart diagram. The speed of this movement depends on mass, and we can actually identify real stars along these paths. Alright, now let's take a closer look at what actually happens when stars move across the chart diagram to their sizes and temperatures. So this is where the terms giant and supergiant come into play. Now medium mass stars like our Sun expand dramatically once hydrogen in the core is exhausted. Take Aldebaran for example. Its diameter is about 40 times that of our Sun. And that's huge. But notice its surface temperature is cooler than the Sun's. So it glows red instead of yellow-white. So this is a perfect illustration of how core contraction and shell hydrogen fusion push the outer layers outward, making the star enormous and less dense. Now massive stars take this expansion even further. They become supergiants and their properties are even more extreme. Now Betelgeuse is an iconic example. About 700 times the diameter of the Sun and quite cool on its surface, giving it that deep red glow. And Rigel is different. Its surface temperature is around 12,000 Kelvin. So it appears blue, but it has also expanded. Its diameter is 75 times the Sun's. So even though Rigel looks blue and hot, it's actually cooler than it was on the main sequence. So the expansion dominates its evolution, not just its color. Now whether a star becomes a red giant or a blue supergiant, both go through envelope expansion and surface cooling. For blue giants like Rigel, the color difference is really just a reflection of surface temperature, not the direction of evolution. And they have expanded and cooled compared to their main sequence state, even if they still appear hotter than red giants. So in summary, stars become giant or supergiants depending on their initial mass. So expansion is the key, and cooling of the surface gives us the red or blue colors we observe. Okay, now that we have looked at how stars expand into giants and supergiants, let's explore why these stars become so large and why they are relatively uncommon in the night sky. So when a star's outer layer expands, the mass of the stars is spread over a much larger volume. Now you can imagine taking a basketball and inflating it until it's the size of a stadium. And that's the kind of scale we are talking about. Because the same amount of mass is now spread over such a huge space, so the density drops dramatically. Which is why giants and supergiants have such low densities compared to the main sequence stars. Next, let's see what this expansion means for their placement on the chart diagram. Interestingly, stars of different initial masses all end up in roughly the same part of the chart diagram once they evolve into giants. And this is why giants and supergiants cluster together rather than forming a neat mass-dependent sequence. And it also explains why there isn't a simple mass-luminosity relation in this space. The star's brightness are more dominated by the expanded envelopes and energy output from shell fusion than their original mass. Now finally, let's summarize what's happening inside the star as all this expansion takes place. The core contracts and heats, while the envelope expands and cools. Then the star becomes much brighter because of the large surface area. But this phase is relatively short-lived, especially compared to the long, steady life of a main sequence star. And this short lifetime is another reason why giants are less commonly seen. Stars spend far less time in this phase than on the main sequence. So to recap, the enumerous size, low density, clustering on this chart diagram, and short-lived nature all explain why giants are so large and rare. Right. Now that we understand why giants are so large and rare, let's dive deeper into the core of these stars. So the core's behavior is key to understanding some of the most dramatic events in stellar evolution. And this brings us to degenerate matter. Now as the star expands into a giant, its helium core contracts under gravity, becoming incredibly dense. Now to give you a sense of scale, imagine if the core were the size of a baseball. The outer envelope of the star would be the size of a stadium. And that's how small and dense the core is compared to the rest of the star. So this extreme compression is what sets the stage for the unusual physics we will see next. Now, when the core gets this dense, quantum mechanics takes over. Electrons inside the core can only occupy specific energy levels, like the rungs on a ladder shown in this figure. And remember the Pauli exclusion principle. It prevents two identical electrons from occupying the same level. So in a degenerate core, almost all the lower rungs are filled, and electrons cannot just move freely as they would in a normal gas. Now here on the left, low density gas has many open rungs, and on the right, high density degenerate gas has nearly all lower rungs filled, which causes the unusual properties we are about to discuss. So this gives rise to two very unusual behaviors. It resists compression extremely strongly, even harder than steel. Although you can push on it, it barely shrinks. And its pressure does not depend on temperature. Normally, heating a gas makes it expand. But in degenerate matter, adding heat doesn't change the pressure much at all. Now these properties are crucial for understanding how certain stars experience sudden helium flashes. So why does this matter? Because degenerate cores set the stage for helium fusion bursts in medium mass stars. And eventually, when stars run out of fuel, these degenerate cores can survive as white dwarfs, essentially a stellar remnant supported entirely by electron degeneracy pressure. So degenerate matter is one of those strange counterintuitive concepts where quantum mechanics really rules the behavior of macroscopic objects, and in this case, the heart of a star. Alright, now that we have explored degenerate matter in giant star cores, let's see what happens when helium finally starts to fuse. And this is the next major stage in stellar evolution, helium fusion, which is quite different and more challenging than hydrogen fusion. Now, helium fusion is not as simple as hydrogen fusion. Helium nuclei have 2 protons each compared to 1 proton in hydrogen. And that means the Coulomb barrier, the repulsion between positively charged nuclei, is much higher. So the star's core must reach about 100 million Kelvin for helium nuclei to collide with enough energy to fuse. And that's almost 10 times hotter than the core during hydrogen fusion. Now looking at this figure, you can see the tiny helium core of a 5 solar mass red giant, magnified 100 times. Now even though the core is small, it's intensely hot and dense, and surrounding it is the hydrogen fusion shell, which continues to add helium ash to the core while the outer envelope expands and cools. Here, notice the tiny inner core below 0.1 solar radius and the hydrogen shell above it. and the outer layers that make the star appear so enormous compared to the sun. Okay, now how does helium fuse into carbon? So this happens through the triple alpha process. Two helium nuclei first collide to form beryllium 8 nucleus, which is extremely unstable. Then a third helium nucleus must collide with that beryllium 8 nucleus before it breaks apart, forming a stable carbon nucleus. And because this requires a precise series of collisions in a very short time, it's a rare process. But over millions of years, it builds up significant carbon inside the core. Now, the energy released in helium fusion is dramatic. In fact, the second step of the reaction produces roughly 80 times more energy than the first step absorbs. And this energy powers the star and helps maintain the balance between the core's contraction and the expansion of the outer layers. So even though the core is small, the triple alpha process has a huge impact on the star's luminosity and its path on the HR diagram. Now look at the image again. The energy released in the core influences the huge outer envelope of the star, keeping it puffed up as a red giant, while helium steadily converts to carbon inside. Okay. Now let's see an even more dramatic scenario, the helium flash, where helium fusion ignites explosively in stars with degenerate cores. And this is a spectacular but hidden event inside the heart of a star. And understanding it really shows why degenerate matter is so important. Now in stars with medium masses, the helium core becomes degenerate. Remember, degenerate matter has the strange property that pressure does not depend on temperature. But normally, a star's fusion reactions are regulated by a pressure-temperature thermostat. So if the core gets hotter, it expands, the temperature drops, and fusion slows. But in a degenerate core, this thermostat fails. So when helium finally ignites, the rise in temperature accelerates the fusion reactions, causing a runaway explosion inside the core. And it's like trying to turn on a heater with no thermostat. The temperature just keeps rising uncontrollably. Now here you can see the HR diagram showing the helium flash region for medium mass stars. Notice how stars around 1 to 3 solar mass experience this flash, while more massive stars ignite helium smoothly and lower mass stars never get hot enough. So even though the energy release is enormous, comparable to the combined luminosity of all the stars in the Milky Way, the star itself is not destroyed because most of the energy hits the tiny core or is absorbed by the already expanded envelope. So from the outside, the star hardly shows any eruption. And the flash happens in seconds to minutes. And quickly, the core ceases to be degenerate. And after that, the normal pressure temperature thermostat takes over and helium fusion proceeds steadily. Now the helium flash doesn't happen in all stars. Stars around 0.5 to 3 solar mass experience a helium flash, and stars less than 0.4 solar mass never get hot enough to ignite helium. And stars above 3 solar mass ignite helium gradually without a flash because their cores are already hot enough before degeneracy sets in. So whether a star flashes or not really depends on its mass, which is why the helium flash is mostly relevant for stars like our Sun. Again, look at the red zero edge main sequence in the chart diagram. Here, the evolutionary tracks for 1 and 3 solar mass show the helium flash zone clearly, and stars above 3 solar mass skip this violent stage. Alright, now having seen the dramatic helium flash, let's now explore what happens after the flash. when the star settles into a more controlled phase. So this is critical because this state shapes the star's future evolution and the elements it produces. Now immediately after the helium flash, the helium core expands due to the huge energy release. And as it expands, the gas ceases to be degenerate, meaning the pressure temperature thermostat is restored. Now the star can control helium fusion in the core. So fusion no longer runs away uncontrollably. It proceeds at a steady rate. And this is important because the helium fusion produces carbon and oxygen, which will accumulate in the core over time. Now here you can see the evolutionary track of a 3 solar mass star. The first giant stage has an inert helium core, and the helium flash occurs when the core ignites. Next, after the flash, notice the core expand, and the subsequent stable helium fusion occurs in the second loop of the red giant region. Now while the core stabilizes, the outer envelope responds, and the previously expanded layers contract slightly, which increases the surface temperature. Next, at the same time, the star's luminosity recovers to a new equilibrium. So even though the star went through a violent flash, it now behaves like a stable, bright red giant with the core fusing helium and an envelope reacting to the new energy balance. Now the envelope contraction and temperature rise may seem subtle, but it's key for the star's position on the HR diagram. So looking at the HR diagram, the star loops in the red giant region. Initially it moves up and right as hydrogen is exhausted and the star expands. Next, after the flash, it loops back slightly leftward as the core expands and helium fusion stabilizes. Now during this phase, the carbon-oxygen core grows steadily, and eventually this core will become the heart of a white dwarf in medium mass stars, or it may later fuse heavier elements in more massive stars. Now in the HR diagram, notice the multiple loops. These reflect transitions between hydrogen shell burning, helium core burning, and later helium shell burning. So the star's path is not a straight line, and these loops capture the dynamic response of the star to changes in its core and envelope. So post-helium flash evolution is a return to stability, but with a fundamentally changed interior, a carbon-oxygen core surrounded by helium and hydrogen fusion shells. Alright. Now that we have seen how stars stabilize after the helium flash, let's look at what happens in more massive stars when fusion goes beyond helium. So this is where stars really become factories for heavier elements. Now to fuse elements heavier than helium, a star must reach extremely high core temperatures. And only stars with masses greater than about 8 times the Sun can achieve roughly 600 million Kelvin needed for carbon fusion. And next, once the core is hot enough, the star can sequentially fuse carbon, then nitrogen, oxygen and silicon, gradually building up the heavier elements. And this is why only massive stars can produce the full range of elements needed for planets and life. Now see the figure. Here the network of carbon fusion reactions is illustrated. You can see how carbon-12 can capture additional nuclei to form elements like neon, oxygen, magnesium and eventually silicon. Now here the arrows represent different reaction pathways, some involving protons, neutrons or helium nuclei. Don't worry, you don't have to remember any of these. Okay. So the fusion of heavy elements is far more complicated than hydrogen or helium fusion. And nuclei interact in many ways, capturing protons, capturing neutrons, capturing helium nuclei or alpha particles, or sometimes splitting or decaying into other nuclei. And these reactions collectively produce elements up to iron, which is the end point of exothermic fusion. And beyond iron, fusion consumes energy instead of producing it. So stars cannot naturally fuse beyond that without a supernova. Now here in this figure, notice the many arrows connecting nuclei. So this illustrates just how many reaction pathways exist in massive stars. So astronomers need a detailed nuclear physics models to predict which elements form and how much energy is released. And finally, a key point about stellar lifetimes. The giant phase is much shorter than the main sequence. For example, our Sun spends 10 billion years on the main sequence, but only about 1 billion years as a giant. Here GYR means giga-year. So 1 giga-year equals to what? 1 billion years. And more massive stars pass through the giant stage even faster. So because of these short time scales, giants are rare in the sky, even though they are very luminous. So this explains why we see many main sequence stars but comparatively few giants or supergiants. So massive stars not only create the heavy elements essential for planets and life, but their short-lived giant stages also shape the stellar populations we observe in the galaxy. Okay, now building on what we just discussed about carbon fusion in massive stars, let's zoom out and look at the full sequence of fusion in massive stars and why these stars are so important in the cosmos. Now to start, not all stars can fuse helium or heavier elements. Stars needed to be at least about 0.5 times the Sun's mass to ignite helium and produce carbon and oxygen in their cores. And stars with masses above roughly 8 times the Sun can reach the core temperatures necessary for carbon fusion. And even more massive stars can fuse neon, oxygen and silicon, producing progressively heavier elements. So the mass of the star determines which nuclear fuse it can access and consequently which elements it can create. Now here's the typical fusion sequence in massive stars. Hydrogen to helium, that's the main sequence stage. And then helium to carbon and oxygen. Next, carbon to neon and neon to oxygen. And then oxygen to silicon and silicon to nickel and iron. So each step requires a higher core temperature because heavier nuclei have stronger Coulomb barriers. And fusion can happen either in the core or in shells surrounding the core, depending on what fuel remains. Now the important thing here is that each reaction produces energy and builds new atomic nuclei, a process called nucleosynthesis. So this is literally how the universe creates the elements that make up planets, oceans and even our bodies. Now even though these massive stars are incredibly luminous as giants or supergiants, their giant phases are short-lived compared with their main sequence lifetimes. And this short duration means that fewer giants are visible in the sky, despite being so bright. So eventually, all stars exhaust their nuclear fuel and gravity takes over, leading to the final collapse. And the fate of the star depends on its mass. So by the time a massive star has fused elements all the way up to the iron, it has transformed its interior into a layered structure of different elements and is nearing the end of its life. And that brings us to the end of section 2, post-main sequence evolution. Now, so far we have explored how stars leave the main sequence, expand into giants and supergiants, experience helium fusion and flashes, and in massive stars fuse heavier elements all the way up to iron. So we also saw how the mass of the star governs which nuclear reactions occur and how long it spends in each phase. And everything we have covered sets the stage for understanding why stars appear the way they do at different ages and how they produce the elements that fill the universe. Alright. Next, we will discuss about star clusters, where we will see how groups of stars provide evidence for stellar evolution and let astronomers test the models we just discussed.